SwayamPrabha. Digital India. Educated India.
Hello everyone. So in the last class we converted the Navier-Stokes equations to wave number space, and we briefly looked at what that means, right? So if we converted the Navier-Stokes equations into wave number space, we have a set of ODEs. So potentially you could solve them and get the velocity in wave number space as a function of the wave number vector. So for each wave number, you would have a velocity associated with it. Using that, instead of getting all that information, what we are mostly interested in is, say, for example, the kinetic energy for the different Fourier modes. So using the velocity information, we can get the kinetic energy from the covariance information. We get the kinetic energy for each Fourier mode, and if you sum it up over all the wave numbers, you get the total kinetic energy. You could do the same thing for the dissipation rate as well. You sum it up over all the wave numbers, you get the total dissipation rate. Of course, the equation is slightly different. Now here we are going to look at the kinetic energy spectrum, the kinetic energy for each Fourier mode in a bit more detail and see where that is actually coming from. That is what is covered in this module mostly. We will then later go on to things like the model spectrum and then look at the inertial subrange in the context of these wave numbers. So this here again, this is part of the scales of turbulent motion module. These are the topics that are covered. We will look at the velocity spectrum tensor, as we call it, the energy spectrum function, which is basically the energy spectrum for each Fourier mode. Then we will look at the 1D spectra, what does that mean? The Kolmogorov spectra. We will look at a model spectrum that can tell us a lot about how the flow will behave in terms of the wave numbers. We will look at the dissipation spectra, so that is the spectra associated with the dissipation rate. The inertial subrange, we know what an inertial subrange is now, but here in this module we will study that in terms of the wave numbers and what does that mean in terms of the different energies in the different wave numbers. The energy containing range, of course, those are associated with the anisotropic large scales. And then we will look at, in more detail, a spectral view of the energy cascade, look at an energy spectrum balance through an equation, and look at some limitations of analyzing these flows through wave numbers and see what that means. All right, so again, all of these notes are indeed from Pope's book. Now, what does a velocity spectrum tensor mean? So in homogeneous turbulence, so what does homogeneous turbulence mean? Statistically, there is no variation with space. Everything is, you have a single value. You vary with space, there's no statistical variation with space. So that's what homogeneous turbulence is. And then you have the 2-point velocity correlation. You already know what that is. We represented it as Rij, if you remember, Rij. Now the 2-point velocity correlation and the velocity spectrum tensor form a Fourier transform pair. Essentially, the velocity spectrum tensor is the Fourier transform of the 2-point velocity correlation. Rij is ui times ui of x comma t times uj of x plus r comma t, isn't it? Rij. Again, I am not putting the exact mathematical definition, but at least you need to understand what the basic idea of a 2-point velocity correlation is. It's basically ui of x comma t times uj of x plus r comma t. So r is the spacing between the 2 points. ui and uj, j could be different from I, j could be the same as I. That forms your tensor rij. If you have r11, then you have u1, u1. If you have r12, you have u1, u2, so on and so forth. Of course, it depends on the spacing as well, as in the spacing between the 2 points, so r. So rij will be a function of r as is shown here. R would be a vector. I'm not talking about capital R, I'm talking about small r, which would be a vector, just like x is a vector. So rij of r. And if you want to take a Fourier transform, this would be a 3D Fourier transform, because rij is a 3D variable. It's a tensor, and each component in that tensor is a 3D variable. So when you take a Fourier transform, it would be a 3D Fourier transform. Minus infinity to infinity, by definition 1 over 2 pi cube rij of r e to the minus I kappa r. So this is your velocity spectrum tensor phi ij of kappa. So very complicated, because if you take your velocity, 2-point velocity correlation itself, think about it. We are talking about a variable that is 3-dimensional, in fact 4-dimensional, because it depends on time, but you're also saying that it has 9 components related to the different components of the velocity. So you have r11, r12, r13, r21, r22, r23, and so on. And so this, you are taking if you take a Fourier transform of this, obviously your Fourier modes are also going to be a tensor. That is why we have a velocity spectrum tensor, terming it as phi ij of kappa. And obviously the 2-point velocity correlation is the Fourier inverse, is the inverse Fourier transform of the velocity spectrum tensor. As you know, kappa is a wave number vector given by kappa 1, kappa 2, kappa 3. It's a continuous wave number vector. And r is this the lag or lead between the 2 points. Now, the velocity spectrum tensor basically represents the Reynolds stresses. It represents the Reynolds stress in wave number space, isn't it? Phi ij is the contribution, of course, per unit volume, because you have now divided it by volume 1 over 2 pi cube, from the Fourier mode e to the I kappa dot x to the Reynolds stresses ui uj. Ui uj mean is the Reynolds stresses. Essentially, the velocity spectrum tensor, the physical significance is, it is the Reynolds stress in wave number space. That's what it is. Now, if you set r is equal to 0, that means you are taking the covariance with respect to a single point. So then what you have is rij of 0. So that is in fact technically the Reynolds stresses. The Reynolds stresses takes the covariance at a single point. The original 2-point velocity correlation could take it between points that are further. So you have ui uj mean. Rij of 0 is ui uj mean, which is the Reynolds stresses. So if you substitute r is equal to 0 here, what you get is triple integral phi ij of kappa d kappa. So it's a triple integral phi ij of kappa, isn't it? You just substitute r is equal to 0 here. So then what you have is phi ij of kappa d kappa. Now, phi ij, the velocity spectrum tensor, think about it. The information contained in phi ij can be considered in 3 parts. The first part is the subscript I and j give the directions of the velocity, u1, u2, u3, u1, u2, u2, u3, so on. And then the wave number, because it depends on kappa, the wave number direction, which is kappa over kappa magnitude. That's what it is. Kappa over kappa magnitude. That is the wave number direction alone. Kappa is the wave number vector. Kappa bold is the wave number vector. And kappa over kappa magnitude is the direction alone. So since the phi ij depends on the kappa, it obviously gives information about the direction in the physical space of the Fourier mode. About the direction in physical space. Third, the wave number magnitude, because if you think about this wave number vector, the wave number vector has three components, kappa 1, kappa 2, kappa 3. This will give you the direction, but it also has a magnitude. What does the magnitude represent? The magnitude represents the length scale. So the wave numbers magnitude represents the length scale of the mode. So essentially L is 2 pi over kappa magnitude. So just like any vector has a magnitude and direction associated with it, so does the wave number vector. So the wave number direction, as in kappa over kappa magnitude, gives the direction in physical space of the Fourier mode, whereas the wave number magnitude gives information about the length scale. So three pieces of information alone from the velocity spectrum tensor alone. One is obviously the different directions of velocity, right? U1, U2, U2, U3, U1, U3, so on and so forth. Wave number direction, that gives you the direction of the Fourier mode, and wave number magnitude, that gives you information about the length scale. So that's your velocity spectrum tensor, heavily loaded quantity, isn't it? And then you have the dissipation rate. Now if you consider the dissipation rate, that can be obtained from the velocity spectrum tensor, obviously by taking the same component of velocity. So that is phi I. And there would be a 2 nu kappa squared phi I d kappa integrated over all wave numbers, and then you have minus infinity to infinity. I hope this is clear. So that's the dissipation rate. Now, once you have the dissipation rate, let's think about this energy spectrum function. Now, as I was saying earlier, the velocity spectrum tensor is a heavily loaded function. The velocity spectrum tensor is a heavily loaded function. However, something that is a little bit more simple would be the energy spectrum function, denoted by E of kappa. As you can see, I am considering the energy associated with each wave number magnitude. I am not even taking it as a function of the wave number vector, because that would also have a lot of information. We want to assess a quantity that is relatively simpler, and the energy spectrum function is something like that. So if you take E of kappa, meaning kappa being the magnitude, what you are saying is you are considering the energy associated with each wave number magnitude. Now where does the wave number magnitude come from? We will see this. So you have the energy spectrum function, which can be obtained from the velocity spectrum tensor. By doing what? By removing all directional information about the velocities and just considering half the trace. So that would be half phi I. Why is the half there? Because kinetic energy is half u squared, right? Kinetic energy per unit mass. So that is why you're taking the half phi I. So you're taking half of the trace, because you have u1, u1, right? That's the first term. u2, u2, or u2 squared, and u3, u3, or u3 squared. So half of u1 squared plus u2 squared plus u3 squared. That is why you are taking half phi I of kappa. Now, and what you're doing is essentially you're just taking out all directional information, right? The first part of the velocity spectrum tensor, like we talked about in the previous slide. You're taking out all the directional information and collapsing everything. Now, the information about the direction of the Fourier modes, as in what? The wave number direction, which was kappa over kappa magnitude. You remove all that by integrating over all wave numbers of magnitude. Kappa is equal to kappa magnitude. Kappa is equal to kappa magnitude. Now, what does this mean? How do you do this, right? So think about the wave number space being a sphere. Okay, why am I saying it depends on a sphere? And so if you think about it, kappa magnitude is so let me start by defining the wave number vector, which is kappa 1, kappa 2, and kappa 3. So the wave number magnitude is kappa 1 squared plus kappa 2 squared plus kappa 3 squared, square root. This is like a radius of a sphere, isn't it? So in that sense, what if we consider a sphere? Okay, what if we consider a sphere S? And I'm drawing it like a circle, but you get the idea, which has a radius kappa magnitude given by, in 3D space, square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared, isn't it? That is what we are saying here. So we denote S of kappa, the sphere in wave number space, centered at the origin with a radius kappa as in magnitude, and integration over the entire surface would be denoted by the integral dsk, ds of kappa. So if you want to take the energy spectrum, you can just take E of kappa as half phi I of kappa over the entire sphere, S of kappa. That's what you're doing. What you have done is you have taken out all the directional information by just taking the trace. Taken out all the directional information. You're only taking by taking the trace. So u1 squared plus u2 squared plus u3 squared, which is phi I, multiplying by the half because it is kinetic energy. And then what you're doing is you are collapsing all the information associated with each wave number magnitude into one value. So essentially you are taking each wave number magnitude. So I'm going to draw the sphere again like a circle, and what I'm saying is, if this is the wave number magnitude, I'm just going to write it as kappa. If I don't write the arrow on top, I am denoting it as a wave number magnitude. And let's say that is the radius, right? So let's say I have a shell, and again you have to think of it as a sphere, but I'm drawing it as a circle. So this shell has a radius kappa. This shell has a radius kappa, and I am taking all the velocity information associated with the Fourier modes in this shell. So this shell has a thickness d kappa, and I am taking all information that is contained within kappa that has a radius kappa plus d kappa. You understand what I mean? So what I'm doing is I am taking out all the directional information by collapsing all the information associated with velocity into a single wave number magnitude, into a single wave number shell. That is what I'm doing. So the properties essentially of the energy spectrum function follow exactly what you had for the velocity spectrum tensor. Nothing different. For example, Ek is real, it is non-negative, and for negative kappa, it is undefined or zero. It will always be real. So if you integrate E kappa for all the wave number magnitude, it is same as integrating half phi I over the entire wave number vector. So E kappa d kappa is basically the contribution to the kinetic energy. E kappa, as in E of kappa, is the energy spectrum function. It is the contribution to K from all the wave numbers contained in the shell, kappa to kappa plus d kappa, isn't it? This is kappa, and this right here is kappa plus d kappa. So you have kappa magnitude less than or equal to kappa plus d kappa and greater than or equal to kappa. That is what it is. You are taking all the Fourier modes within that shell, and then you are integrating it. When you integrate it over all the wave numbers, you get a single value, which is the kinetic energy. So K is 0 to infinity, meaning what? Integrated over all wave number magnitudes, E kappa d kappa. But what is E kappa d kappa? It is the energy associated with the wave number shell. It is the energy associated with the wave number shell alone. You integrate that to get the entire kinetic energy. Again, the energy spectrum function E of kappa is the energy associated with a single wave number magnitude. You have obtained that by getting rid of all the directional information. You have collapsed K1, K2 and K3 into a single value. Associated with the wave number magnitude. That is how you get E of kappa. And then to calculate the kinetic energy, you divide your sphere into multiple shells, and for each shell you calculate the energy, and then you add all those up to get the total energy. That's essentially what you're doing. So E kappa d kappa is the energy associated with a single shell. If you integrate it or sum it up over all the shells, you get the total kinetic energy. So you have the total kinetic energy, which is E kappa d kappa 0 to infinity, and the dissipation rate, which is 0 to infinity, 2 nu kappa squared E kappa d kappa. You already knew that, right? Earlier we wrote an equation where we took the velocity spectrum tensor, but now what we are doing is we are considering it in terms of the energy spectrum function. So of course the velocity spectrum tensor, the word I used earlier was a loaded function. It has a lot of information, and sometimes that is difficult to analyze because it has this multiple components, it has this directional information, it has this length scale information. Can we get something a little bit simpler? That's how we started with the energy spectrum function. We started with the energy spectrum function. We took the energy spectrum function, which was the energy associated with each wave number magnitude. How did we get wave number magnitude? Because we got rid of the directional information. We collapsed kappa 1, kappa 2, kappa 3 into just a wave number magnitude, which is given by the square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. This is like a radius of a sphere. So if you think of your wave number space as a spherical space, if you think of your wave number space as a spherical space, then you have this wave number magnitude being equal to, kappa 1, kappa 2, kappa 3, isn't it? You have this wave number magnitude being equal to the radius of that sphere, isn't it? In this sphere. So it is kappa, which is the wave number magnitude, square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared. And that's what it is. That is why you are considering a spherical space. So this wave number space you consider it to be a spherical space. And then what you do is, once you do that, then you can think of your energy spectrum function E of kappa being the energy associated with that single wave number magnitude. So, mathematically one would calculate that by taking all the Fourier modes associated with kappa 1 and kappa 2 and kappa 1, kappa 2 and kappa 3 in such a way that square root of kappa 1 plus square root of kappa 1 squared plus kappa 2 squared plus kappa 3 squared is equal to that particular wave number kappa. That particular wave number kappa, that is what we are doing here. Once you get E kappa, then you want to integrate that to find out what the kinetic energy is. But before integrating, you should know what the physical significance of E kappa d kappa is. It's essentially the energy associated with each shell that has a thickness of d kappa. All the energy in that shell with the thickness d kappa is associated with E kappa d kappa. And the sphere being made up of multiple shells, if you just add the energy of each of those shells, you eventually get the kinetic energy. Same goes for dissipation, except the equation is different. You have 2 nu kappa squared E kappa d kappa. So we started with the velocity spectrum tensor. We saw that it had a lot of information, so we wanted something simpler, and then we went on to the energy spectrum function and eventually into kinetic energy and dissipation. So in the next class, now that we have had the energy spectrum function, we will now use that to define the 1D spectra, We will compare the spectra in the different directions. We will look at the Kolmogorov spectra and eventually the model spectrum as well. Thank you.